Okay, in the previous lecture I had mentioned that the scalar product like psi of phi is not equal to always, like in some cases, like if psi and phi are real number, then psi phi is equal to phi psi, the scalar product. If psi of phi are real, but if psi and phi are not real, then psi of phi is not equal to phi of psi. The scalar product of psi with phi is not equal to the scalar product of phi with psi, and we have to prove it because psi of phi is equal to psi steric phi, while phi of psi is equal to phi steric psi, and these two equations are not equal. So we can easily prove it that the scalar product of psi with phi is not equal to the scalar product of phi with psi. Another property is that the scalar product psi with phi is equal to the scalar product of phi with psi if we take the complex conjugate of this whole product, and we already proved it here. Okay, now there is another property which tell us that the scalar product, if we have two functions psi and phi belongs to the Hilbert space, then the scalar product of psi with phi is linear with respect to second factor. What it means? It tells that psi a of phi 1 plus b of phi 2 is equal to just a psi of phi 1 plus b psi of phi 2. We have to just take out this a from the scalar product of the first with the first, and then we take out b from the scalar product of this psi with phi 2. But on the other hand, the scalar product of psi, the scalar product of psi with phi with phi is non-linear with respect to the first factor. What it means? For example, if we have two functions a of phi 1 plus b of phi 2, okay, and taking the scalar product with psi, then how we will multiply it? We'll multiply this with this and this with this, and then we'll take a summation a phi 1 over psi 1 plus b phi 2 over psi 2. Now how we will represent it in terms of scalar product? We take the a phi 1 steric. For example, psi of phi is equal to psi steric phi, taking the complex conjugate of the first and then multiply it with the second. So here we take the complex conjugate of this one and multiply it with psi 1 plus taking the complex conjugate of the first one and then multiply it with the second one, psi 1. Okay, psi 1 or just psi, okay, no psi 1 or psi Now this is equal to a steric. It's a scalar number. Phi 1 steric, psi 1, psi 1 no, psi, plus b steric, phi 2 steric into psi. Now this is equal to a steric, phi 1 psi, okay, plus b steric, and this is equal to phi 2 psi. So it means that the scalar product of psi with phi is non-linear, because it's non-linear. It's not equal to this one, a psi over phi or b psi over phi 2, because it's a complex scalar number now. Here it was a real number, and here it's a complex number now. Complex conjugate, sorry. So it means that the scalar product of psi with phi is non-linear with respect to the first vector. This was another property. And we have the third property, which tells that the scalar product, this is another property, the scalar product of a vector, no, of a function with itself is a positive real number. What it means? It means that if we take the scalar product of psi with psi, we get psi steric psi, which we normally represent by psi magnitude, and this is always equal or greater than 0. It is equal to 0 if psi is equal to 0, and it is always greater than 0 if psi is not equal to 0. This is another property. This property tells us that the scalar product of psi with psi, a function with itself, is always a real, positive real number. The third property of Hilbert space is Hs. The Hilbert space is separable. What it means? It means that there always exist a Cauchy sequence which I represent by psi n, belongs to the Hilbert space, okay? In each Hilbert space there exists a Cauchy sequence where n is equal to 1, 2 and so on, such that n we have a number which I represent by epsilon, which is greater than 0, such that for every psi belongs to the Hilbert space, there exists one Cauchy sequence psi n, for which if we take the scalar product the difference of this psi from this Cauchy sequence, and taking the magnitude, we always get a number which will be less than this epsilon, and we define the epsilon to be greater than 0. So the difference of every function psi minus the Cauchy sequence will give a number which will be smaller than this epsilon. This means that H is separable. And there is another property which we call that the Hilbert space is complete. It also says that for every Cauchy sequence psi n which belongs to the Hilbert space converges to an element of Hilbert space. What it means? It means that we have consider two Cauchy sequence psi n minus psi m. We take the difference and then taking the magnitude, which is always equal to 0. This relation defines a unique limit psi belongs to H such that if we take the difference of psi from the Cauchy sequence psi n, but we have to apply the limit, okay, here limit n m approaches to infinity. So here we have only one n, so we apply the limit n approaches to infinity. This difference will give us 0. So this means that H is complete. So I'm not going into the detail of Cauchy sequence, okay, because you have already studied it, the Cauchy sequence. In your mathematical method course. So just revise that course, learn about Cauchy sequence, and then see these two properties of Hilbert space. You will easily understand it. Okay, thank you. This is the end of vector space and Hilbert space.